Okay, so now we're going to move into bonding and looking at the shapes and the way things go together. And this is just going to take some practice, which is what we're going to work on in class. But it's just going to take some practice until we learn and understand how it all comes together. Yesterday, or the other day, we started talking about single, double, and triple bonds. It wasn't officially in the notes, but you know, it starts to get, show up in some of the problems. So a single bond is when a single pair, and the key word is pair, of electrons is shared. So that's our 2 electrons, and that's, what we're talking about when we're doing something like H and then F, okay? So we have this one pair of electrons being shared. In a double bond, and that's showing you here in the hydrogen example. In a double bond, we're looking at 2 pairs of electrons being shared. And so that's something like oxygen. Each oxygen is in group 6, and they each contribute 6 electrons. And so just to give you another little sketch of what that looks like. So if each of them have 6 electrons, I have a total of 12. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. And then by doing that, each of these ends up with 8. So this guy has these 8, and this guy has these 8. And then a triple bond is the same thing. It's sharing 3 pairs of electrons, or 6 electrons. So nitrogen here, it's sharing 6. And in order for this drawing to be correct, we really need these electrons still here. So nitrogen each contributes 5, and so that's a total of 10 electrons. So in the middle here, I have 1, 2, 3, 4, 5, 6, and then 7, 8, and then 9, 10. And so they each have 8 around them. If your diagram is not working where everyone has the proper number of electrons, the hint is to start looking at this or this to solve your problem. In a coordinate covalent bond, one element must contribute an unshared pair in order for both elements to be happy. I don't want you to get hung up on the name so much as just to realize that it doesn't always work out to be a perfect puzzle like we have here. So we have CH4, we have 1, 2, 3, 4 electrons, and then 4 hydrogens just come in ever so nicely and dock right in. So if I look at something like carbon and oxygen to try to put them together to make carbon monoxide, if I this guy gives 2 and this guy gives 2, I look at it, well, this oxygen here has 8 because I have 4 and the 6. This guy has 8, but this guy here only has 6. And so that doesn't work to make it happen. So instead, if I still combine those same 2 elements, that means I don't have enough. If I go ahead and make 3, a triple bond in here, and then here. So now I'm looking at a total of 1, 2, 3, 4, 5, 6. So I have a total of 10 electrons. And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And everybody has 8. And so therefore it's happy because everyone has 8. Okay? Polyatomic ions are atoms that are covalently bonded together that gain or lose electrons as a group. So they're ions, but this part of them here is covalently bonded. And so nitrogen is covalently bonded to 3 oxygens, which is why it stays together and it doesn't fall apart. But they gain and lose that electron as a group. So if I look at nitrate, I have nitrogen, which has 5 valence electrons. I have oxygen, which has 6 valence electrons, but I have 3 of them. So I have 5 plus 6 times 3. And then I have 1 extra electron. I still have to add that in there. So 18 plus 5 plus 1 gives me 24 total electrons to work with. When I attack drawing things, I go for the simplest. Single bonds are the simplest. And so because N is my first element, it's my central element, I'm going to put oxygen, oxygen, and oxygen. This nitrogen doesn't have 8 electrons, so I'll go ahead. So I have 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Uh-oh. This guy has 8, this guy has 8, this guy has 8, but my last little oxygen over here does not have 8 electrons. all of a sudden I have no more electrons to add to make this work, so that's my cue. Okay, I need to double bond. So I'm going to take electrons from someone who he's already sharing electrons with, which is nitrogen. So I'm going to move these 2 electrons down here. So by moving them, they then become erased. And now I still have my total of 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, but now everyone has 8 electrons. Because there's an overall -1 charge, I'm going to put it in parentheses and put a negative or a -1 to indicate that there's an extra electron in that ion. Now, bond dissociation energy is the amount of energy required to break a covalent bond. Covalent bonds are stronger than ionic bonds, and triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. And so looking at this, it's just the fact that when we have triple bonds, when we have 6 electrons being shared, it's going to be really hard to break that apart, and it's easier to break apart single bonds. Resonance structure is another term that students are confused by, but it's pretty easy. That means there's 2 or more valid electron dot formulas for a molecule. So I have oxygen, or ozone, which is O3, okay? Ozone has, each oxygen contributes 6 electrons, so 6 times 3 gives me 18 total electrons. If I go to draw this, and I just happen to know that it has a double bond and a single bond, which you would get by trial and error, but I want to make sure that we have enough time to get through these notes, because I want to show you the resonance structure, is here I have my 18 electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, okay? The resonance structure means that it doesn't matter which one of these is the double or the single bond, so it could also look like this, which would be exactly the same thing, sort of a mirror image. And the resonance structure means that I can draw it a different way and it's still the same thing. You typically only have a resonance structure if you have a double or triple bond in there. Now, bonding and shape, and this is a key part of this whole thing. So, A refers to my central element, and X refers to any element that is around the central element. E refers to electron pairs, and more specifically, lone electron pairs. So AX4, an example of that is CH4. And so I have my C in the center, and I have all of my H's around it. But this is not a flat plane. This is not something that's just flat like that. It's three-dimensional. And so the shape of it is tetrahedral. We are still going to draw it like this because it's too cumbersome to draw it, but really what we're looking at is something that's here and here, and then we'll draw this one bigger because it's like coming out towards us, and this one will make a dashed line because it's sort of going back. And we will look at some three-dimensional models of this in class, but all of these angles in here are the same. They're all 109.5 degrees. And so that's our example for tetrahedral. Sometimes we have, and CH4, so C is the A and H is the 4. So if we can match up our formula to this AX scenario, we can then know what the shape is. So if I have something like NH3, if I draw that, it's NH, H, H with a lone pair. N is my A, H, those are my XXX, there's 3 of them, and then a pair of electrons. We don't see electrons, but they still take up the space. So for example, it's like having this prong here taking up space, but it's unable to be seen. We call this shape trigonal pyramid, and it's going to look something like this if I sketch it in 3 dimensions. And then there's my electrons that we don't see, but that's the shape. It's a pyramid shape in here if I were to connect this, okay? Then, if I have something like AX2E2, so I'm going to have a central atom, I'm going to have 2 things around it, and it's going to have 2 pairs of electrons. My very classic example is H2O, okay? H can't be my central atom because it can only have 1 thing bonded to it, so oxygen is in the middle, and I have H, and I have H, and then it has lone pairs of electrons. And I know I'm sort of just drawing these, and this part's just going to take practice, which is what we're going to do. But I want to make sure we're understanding the shapes here. And so here we have what we call bent, because it's this same structure, but we have 1 pair of electrons, and then we have 2 that we don't see. So we end up with a structure like this, and some electrons here, and some electrons back here that are forcing these out of position, okay? And we will look at some 3-dimensional models in class. So we can only figure out the shape once we have the drawing. So once I have this drawing, I look at it and say, okay, A, X2, E2, bent automatically. Then we have something trigonal planar. It doesn't show up terribly often, and the example we have actually doesn't follow all of the rules, okay? But something like BF3. So B is in group 3, and so it does actually end up that it doesn't have 8 electrons around it. I'm not going to get into total reasons why, but you can have them where they don't have a full set of 8 electrons. A couple elements are okay with that, and we will be exposed to those in class. But those ones will. They're trying to maximize their distance apart from one another. And 120, they are a plane, and we're going to call this trigonal planar. And then, if we do have something where there is a pair of electrons, so we're looking at something like GeF2, and again, this one isn't going to follow the octet rule perfectly, but we'll have GE, which is group 4. So 1, 2, let's put these F's on here. And there's my F's. But basically I have 1 central atom, 2 things bonded, and 1 pair of electrons. It's like taking one of these away. And so it looks like this, and it's a different form of bent. And then my last thing is something like AX2, and I'm going to look at CO2 as my example. So CO2 ends up being like this with double bonds. But I have 2 things around it, and so it's just linear. Okay, so looking at the way these are set up and the way they are put together, the ones that are going to be the ones that are most important to us, that we're going to use the most, is going to be this AX4, this one, and sort of this one. These 2 don't show up quite as often. That doesn't mean they're not valid, but these are the 6 structures that we're going to talk about. There are as many as 12 to 14 different shapes. We're just not going to get as involved in getting those larger shapes together. Actually, we will see this one with some double bonding in there quite a bit. Okay, so if you think about it, knowing what this symbol is and how this relates to what the name of the shape is, that will really help you be able to successfully do this. The drawings are going to come with us working in class and just practicing them.